Welcome to the first lesson of me doing real analysis. This video serves as a proof of concept of this idea. So for this video, we're going to be talking about bijections. So I'm going to assume a knowledge of proof writing and or of introductory proof writing and proof methods, also functions, like what a function is. And then after that is where this lesson will pick up. So first we're going to talk about what is a bijection. So a bijection is a function f from a to b that is both injective and surjective. So if this function is both injective and surjective, it is a bijection. So what exactly is an injection? So an an injection is is also called one-to-one. So a function being an injection or a function being one-to-one is the same thing. So if a function from a to b is an injection, if for every element a in a and a prime in a, if a is not equal to a prime, then f of a is not equal to f of a prime. So essentially, if you have two elements in the domain, then if they're not equal in the domain, then they do not map to the same element. So this also, we can take the contrapositive of this final statement here, and we can equivalently write that f is an injection if for all a and a prime in A or in the domain, if f of a is equal to f of a prime, then a is equal to a prime back in the domain. So this is also sometimes like an example of a function that would not be injective is x squared. F of x equals x squared. So the reason this wouldn't be injective is because we can clearly see, for example, at F4, that you have these two elements, and this is not to scale, but 2 and -2 are both in the domain, but they both map to 4. And so we have this contradiction that f of 2 is equal to f of -2. But 2 is not equal to -2. So again, this would not be an injection. But a simple example of what would be an injection is something like y equals x, or sorry, f of x equals x. Just goes through the middle, and every single element in the range has one unique element that maps to it, namely itself back in the domain space, because the domain and the range are the same spaces. Or sorry, they're both the real numbers. Okay, so then we finally come to what a surjection is. So a function f from a to b is a surjection, also called onto. So f would be called, f is onto also means it's surjective or a surjection, if the range of f is equal to b. So again, look at this example right here, f of x equals x squared. Note that the range of f of this function here is not the entire real number line. So even though f is said to map to the real numbers, it only maps to the positive real numbers, including 0. And because it does that, the range is not all of b. And so we would say that f of x equals x squared is not a surjection. Not a surjection. But remember that we also need to in order to make this claim, the spaces that are being mapped to need to be very clearly defined. So f is going from R to R, or the real numbers to the real numbers, is what we're implying here. If we rewrote it as if f was from R to R positive, union 0, then this would be a surjection. Um, that's not usually how we write that. Note that f of x equals x is a surjection. This is pretty clear to see, just uh, mainly because the entire range is all of R. And to rigorously show that, the point is that, or the method that we go about that is that if we select any element in our domain space, in our codomain B, there exists some element back in the domain space, or in the set of the domain, such that it will map to that element. So we can show this pretty easily with f of x equals x, because if we just choose this isn't rigorous, but if my element in R, if I just chose A in R, let me get green. Sorry. A in R, then what will map to that? Well, since f of A equals A, then we show that for any A and R, we can find some element back in the domain space. Because you just take A and R again. Sorry. This is a little bit um it's a little bit confusing because we're just mapping it to itself. But if I take A and R this time in the domain, then I see that if I map from F to A in the domain, then we get to here in the range for any A and R. So this illuminates for us ideas of cardinality and um, and also for inverses, which we might talk about in another video. But cardinality is like a way to discuss the size of infinite sets. So one really important thing that will be used throughout a lot of real analysis is countability. So a set is countable if you can construct if it is one, if it's finite, or two, if it's not finite, if it's an infinite set, then you can create a bijection from the natural numbers to said set. So for example, both 2n, the set of even numbers, even natural numbers, my apologies, is countable. And so are the set of integers. As a matter of fact, so are the rationals, but that argument maybe will come in another video. So I'm just going to construct a bijection. I'm not going to go about proving it rigorously here, but I can choose my bijection I'm going to choose is f from n to 2n, where we're going to take any n and map it to n. Yeah, so this is simply a bijection. I think actually I will rigorously show this. So let me select for 1-to-1 or injection. Let me select I'm going to use the contraposition that we used here, this equivalent statement. I find it easier to use. But yeah, so we're going to choose some arbitrary a and a prime in the domain space, which is the natural numbers. And then we're going to see what follows if we say that f of a is equal to f of a prime. Note it's also important that these functions are well defined. Although that's whenever we're talking about functions, we're usually always just talking about well-defined functions because there would be a problem if this f or any f that we're talking about maps to or maps to two elements in the codomain, because then we would have like it would just present these like very weird contradictions and it just doesn't follow like anything logical really doesn't follow from there. In talking about injections and surjections. So again, we're going to talk about if we have A and A prime in A, apologies, in N, then if we suppose f of A is equal to f of A prime. And this would imply that 2A is equal to 2A prime, which again just simply applies that A is equal to A prime. So F is injective. Oops, sorry. And then let's do onto. Okay, so for onto, note again, if we just select any element in the codomain, that we can find some element back in the domain that will map to it. So let us choose, let's choose, let's do B into N. So since B is even, by definition, even natural numbers of even B is equal to 2k for some k in N. Thus, f of k equals 2k, which equals B. And as k is an N, we're done. So therefore, f is surjective. So since it's surjective and injective, this is a bijection. A. Okay. So now we're going to do the set of integers. This one I don't think I'm going to go about proving because there are more to do. But for this one, I think I would want to construct my my function as, let's see, for my f from n to z. I'm going to say that if n is even, then f of n equals k. So again, n being the element in the natural numbers. And then if n equals 2k plus 1, then f of k equals negative k. So this is a bijection, and maybe you can like prove that on your own. But now I'm going to go to our example problems that are a bit more theoretical. So for this problem, we have a function f from a to b and a function g from b to c that are both bijections. So we want to show that the composition of these functions, g of f, g composed of f, is a bijection of A onto C. So again, or not again, sorry. F goes from A to B. So we have A and B. And then G takes us from B to C. So this is via G, and this is via F, and then via G of F, or G composed of F. Okay, so to show that this is a bijection, let's again split it into parts. So we're going to split it into the injection part first. So I'm just going to do 1 to 1. Okay, so let us let A1 let A1 and A2 be in A. And then let's assume that G of F of A1 is equal to G F of A2. So this also implies that G of F of A1 is equal to G of F of A2. So since G is injective, because it's a bijection, it implies that it's an injective. Since G is injective, I'm going to shorten it from now on. It follows that F of A1 is equal to F of A2. And since F is injective, this implies that A1 is equal to A2. And so again, we showed that for two arbitrary elements in the domain space, that if they are equal to each other in the codomain set, then this implies that they're equal back in our domain. And so we've shown that. Therefore, G of F is injective. Okay, let us move on to onto. So for a function to be onto, remember that the range is equal to the codomain. So we know that both G and F respectively are surjective. And also note that, so first of all, let's say G and F are surjective. And then we have that G composed with F of some X is equal to G of F of X. Again, let me define this. X is in A, just for some, for all of the X in A in our domain. So from here, we say that since F is surjective, it follows that for all B and B, there exists some A and the big set A such that B is equal to this F of A. And then as G is also surjective, G is surjective, then for all of our C and our big set C, there exists some B and B such that G of B equals G of F there, which equals C. And so we've shown that G of F is surjective. Therefore, G of F is projective. Okay, and now for our final problem. So now we have two functions, f and g, and where f maps from a to b, and then g maps from b to c. So we're going to show that if g composed with f is injective, then f is injective. So it's a similar flavor of what we were doing in the last problem, but this time we're talking about the functions that what is implied from the functions that are composed with each other being injective or surjective, and what that implies about the respective functions that are being composed. So we're given that g of f is injective. Okay. Okay, so my apologies. I got lost in my notes for a second. Okay, so we're given f from a to b and g from b to c, and that okay. So given g of f is injective, it follows that for all x1, x2, and a, if g of f of x1 is equal to g of f of x2, then by definition of composite functions, we have g of f x1 equal to g of f of x2, implying that since they're injective, that x1 is equal to x2. But note that no x1 and x2 are in our domain space. And as shown above, we have shown above that for all elements in our space A, that that f of x1 is equal to f of x2 by the injectivity of g of f. Thus, x1 is equal to x2. Therefore, f is injective. So there's a second part of this problem that I left out intentionally, and that's to show that G is surjective, or is a surjection from B to C. But feel that I should leave that up to the viewer. But yeah, this was my video, my test run. My apologies about losing track of some of my notes and any stuttering. But yeah, goodbye.